Dear students, after studying this module, you shall be able to learn about the structure of boranes, bonding in boranes, and understand the different kinds of bonds in boranes. In this module, we will see how bridge bonding in diborane could be described simply by taking two banana shaped 3-center 2-electron bonds, and understanding of the overall distribution of the valence electrons of diborane requires a molecular orbital treatment by taking into account the symmetry of the whole molecule. The concept of 3-center 2-electron bond can be applied to a variety of other electron deficient compounds. In boron chemistry, 3 types of 3-center 2-electron bonds find considerable applications. The BHB bridge bond, closed 3-center BB bond, and open 3-center BB bonds. Bonding in boranes. The bonding in boranes must logically be taken up with diborane, for which the concept of 3-center 2-electron, that is the BHB bond, proposed by Longet and Higgins, was introduced. The ideas were then extensively developed by Lipscomb and his co-workers. In covalent bonding theory, molecular orbitals are formed by linear combination of atomic orbitals. Example, 2 atomic orbitals of the same symmetry and similar energy combine to form one bonding and one antibonding orbital. In a similar manner, if 3 atomic orbitals of same symmetry and similar energy combine linearly, these would give rise to 3 molecular orbitals. The number of atomic orbitals which combine linearly is always equal to the number of molecular orbitals that are formed. Now, bonding in diborane. In B2H6, we have 2 boron atoms, each with an available orbital having electronic configuration, that is 1s2, 2s2, 2p1 with 3 valence electrons. The structure of diborane is of great interest. The diborane is an electron deficient compound, that is, there are not enough valency electrons to form the expected number of covalent bonds. The electron diffraction and spectral studies have suggested a hydrogen bridge structure in which one hydrogen atom forms a bridge between 2 boron atoms, while the terminal hydrogen atoms form normal covalent bonds with boron atoms. In B2H6, there are 2 terminal BH2 units bonded by 2 bridging hydrogen atoms. In each terminal BH2 unit, there exists ordinary 2 center 2-electron BH bonds. Each boron atom is left with 1 electron after forming 2 bonds with the hydrogen atoms, that is the 2 center 2-electron bond. Let us now consider the bridging arrangement BHB. The bridging hydrogen atom has 1 electron and 1 useful orbital, namely the 1s orbital. Each boron atom also has an available orbital having an electron. We now have two 3-center BHB bonding molecular orbitals containing 4 electrons, of which 2 electrons are contributed by 2 boron atoms after the formation of the BH2 terminal bonds, and 1 from each hydrogen atom. These 4 electrons now occupy the 2 bonding molecular orbitals and the bridge bonding system is completed. An identical 3-center bonding molecular orbital will be formed in the other bridging system, that is BHB. It is assumed that boron atom in B2H6 are sp3 hybridized and form simple 2-center 2 electron bonds to their terminal hydrogens. The 2 terminal BH2 groups are present in one plane and the bridged BHB bonds are present in a plane perpendicular to the plane containing the 2 BH2 groups as shown in figure 1. Since 2 valence electrons of each boron atom are used up in BH2 bonding, the remaining valence electrons of each boron atom is used in the BHB bonding. Thus, each boron atom contributes 1 electron towards the 3-center 2 electron BHB bond. The bonding molecular orbitals involved in B2H6 and the structure of module are represented in figures 1 and 2. Here you can see that there are 2 kinds of hydrogens which are there. 4 of the hydrogens are the terminal hydrogens and 2 of the hydrogens are the bridging hydrogens. It is also clear from the bond lengths and the bond angles formed by these BHB bonds. As already mentioned, the BHB bridges are considered as part of the BN framework. The valence electrons of the 2 boron atoms can thus be accounted for as follows. The total number of valence electrons of 2 boron and 6 hydrogen atoms is equal to 12. Electrons used up in the 2 bridges is 4 and electrons used up in 4 terminal BH bonds is 8. Different bonds in boranes. The following types of bonds are thus assumed to be involved in the bonding in the case of boranes, which is shown in table 1. The electrons involved in the bonding in the framework skeletal structure of BN cluster in boranes are referred to as framework electrons. The BHB bonds are considered as part of the BN framework, whereas the BH terminal bonds are not, although the framework electrons of BN cluster are highly delocalized, that is, they belong to all the boron atoms of the framework. Yet, the localized 3-center 2 electron and 2-center 2 electron molecular orbital approach can explain the main features of the structure of boranes. Each boron atom has 3 valence electrons, of which 1 electron is used up by each boron atom of the framework in the normal 2-center 2 electron terminal BH bond, and the remaining 2 electrons are contributed towards bonding in the BN framework. The table is showing different types of bond possibility in the boranes, and here you can see that 3 center 2 electron triply bridged BB bond, in which one bonding electron originally belongs to the boron atoms. The 3 center 2 electron triply bridged BHB, here both the bonding electrons are originally belonging to the boron atoms. And 2 electron normal BB bond, here one bonding electron originally belongs to each boron atom. And finally, the 2 center 2 electron normal BH bonds, the bonding electrons originally belong to the boron and the hydrogen atoms. However, the boron atoms of each terminal BH2 group contributes 1 electron to the BN framework. Thus, overall bonding in boranes is codified as a 4-digit number called the Stokes number. The first digit represents the number of 3 center 2 electron BHB bonds in the structure. The second, third and the fourth digits represent the number of 3 center 2 electron BBB bonds. Normal 2 center 2 electron BB bonds and the terminal BH2 groups respectively. Now we come to the example of bonding in higher boranes. Bonding in higher boranes, that is B4H10, B5H9, B6H10, B5H11, B10H14. So we will first discuss the bonding in B4H10. The bonding in B4H10 can easily be explained more easily by writing the plane projections of its structures as shown in the following figure. There are evidently 4 BHB bridges, no BBB triple bond bridge, 1 BB bond and 2 terminal BH2 groups in B4H10. Hence, out of the 12 valence electrons of the 4 boron atoms, 4 electrons are used in forming 4 BHB bridge bonds. 2 electrons are used up in 1 BB bond and the remaining 6 electrons are used in the 6 terminal BH bonds. So, the total number of valence electrons of 4 boron atoms is 12. Valence electrons of 10 hydrogen atoms is 10 and the total number of valence electrons of 4 boron and 10 hydrogen atoms becomes equal to 22. Electrons used up in the 3 center 2 electron 4 BHB bridges is 8. Electrons used up in the 2 center 2 electron 1 BB bond is 2 and the electrons used in 6 terminal BH bonds are 12. Bonding in B5H9. The bonding in B5H9 can be explained conveniently by considering the plane projection of its structures as shown in the figure. Out of these 15 electrons of the 5 boron atoms, 4 electrons are used up in 4 BHB bonds and 2 electrons in 1 BBB triple bridge bond and 4 electrons in the 2 BB bonds and remaining 5 electrons are used up in the terminal BH bonds. Total number of valence electrons of 5 boron atoms is 15. Valence electrons of 9 hydrogens hydrogen atoms will be 9 and total number of valence electrons of 5 boron and 9 hydrogen atoms will be 24. Electrons used up in the 3 center 2 electron 4 BHP bridges will be equal to 8 and the 3 center 2 electron 1 BB bridge will be equal to 2. The electrons used up in the 2 center 2 electron BB bond is 4 and electrons used up in the 5 terminal BH bonds will be 10. Now let us come to the bonding in B6H10. The bonding in B6H10 can be explained satisfactorily by considering the plane projections of its structure as shown. That is why we are giving the Stike's number as 4220. Out of the 18 valence electrons of 6 boron atoms, 4 electrons are used up in the 4 BHP bridge bonds, 4 electrons in the 2 BBB triple bridge bonds and 4 electrons in the 2 triple bridge bonds, 4 electrons in the 2 BB bonds and the remaining 6 electrons in the 6 terminal BH bonds. So, total number of valence electrons of 6 boron atoms will be 18, valence electrons of 10 hydrogen atoms will be 10 and the total number of valence electrons of 5 boron and 9 hydrogen atoms will be 28. Electrons used up in 3 center 2 electron 4 BHB bridges is 8. Electrons used up in the 3 center 2 electron 2 BBB bridges is 4. Electrons used in 2 center 2 electron 2 BB bonds is 4. Electrons used in the 6 terminal BH bonds is 12. Bonding in B5H11. The bonding in B5H11 can be explained satisfactorily by considering the plane projections of its structure and the different bond lengths are indicative of this different kind of bonds. B5H11, the Stike's number is 3203. There are total number of 15 valence electrons of 5 boron atoms in B5H11, out of which 3 electrons are used up in the 3 BHB bridges, 4 electrons in the 2 BBB triple bridge bonds and the remaining 8 electrons in the 8 terminal BH bonds. So, the total number of valence electrons of 5 boron atoms is 15. The valence electrons of 11 hydrogen atoms is 11 and the total number of valence electrons of 5 boron and 9 hydrogen atoms is 26. Electrons used up in the 3 center 2 electron 3 BHP bridges is 6. Electrons used up in the 3 center 2 electron 2 BBB bridges is 4 and electrons used in the 8 terminal BH bonds is 16. We come to the bonding in B10H14. In B10H14 there are 4 BBB triple bridge bonds and 2 BBB bent bridge bonds having this structure. Hence, out of the 30 valence electrons of 10 boron atoms, 12 electrons are used up in the 6 BBB bridge bonds, 4 electrons are used up in the 4 BH bridge bonds and 4 electrons are used up in the 2 BB bonds. The remaining 10 electrons are used up in the terminal BH bonds. So, the total number of valence electrons of 10 boron atoms is 30. valence electrons of 14 hydrogen atoms will be 14, and the total number of valence electrons of 10 boron and 14 hydrogen atoms will be 44. So, the electrons used up in the 3 center 2 electron 4 BHB bridges is 8. Electrons used up in the 3 center 2 electron 6 BBB bridges is 12. Electrons used up in the 2 center 2 electron 2 BB bonds is 4, and the electrons used up in the 10 terminal BH bonds is 20. This table is indicating the number and the types of bonds present in some of the boranes. Boranes, valence chain electrons, the bridging 3 center 2 electron bonds, and the closed BBB bonds. So, in diborane we have 12 valence electrons. The bridging 3 center 2 electron bonds are 2. In tetraborane, that is B4H10, there are 4 BHB bonds and there is no BBB bond. In the pentaborane, we see that there are B5H9, we see that there are 4 BHB bonds and there is 1 BBB bond. In pentaborane, that is B5H11, there are 3 BHB bonds and 2 are the BBB bonds. In hexaborane, we find that is B6H10, their total number of electrons are 28. Out of that, 4 are the BHB bonds and 2 are the BBB bonds, which are taking 4 electrons. And finally, in decaborane, that is B10H14, we find that there are 4 BHB bonds and 6 are the BBB bonds. To summarize, it is assumed that boron atoms in B2H6 are sp3 hybridized and they form simple 2 center 2 electron bonds to their terminal hydrogens. Also, the 2 terminal BH2 groups are present in one plane and the bridged BHB bonds are present in the plane perpendicular to the plane containing the 2 BH2 groups. The 2 valence electrons of each boron atom are used up in the BH2 bonding and the remaining valence electrons of each boron atom is used up in the BHB bonding. Thus, each boron atom contributes 1 valence electron towards the 3 center 2 electron BHB bond. The 2 electrons responsible for the formation of a 3 center 2 electron bond, that is the BHB, will occupy the bonding molecular orbitals. The number and types of bonds in B2H6, B4H10, B5H9, B6H10, B5H11 and B10H14 are summarized in table 2. As we can look at the qualitative diagram or picture of bonding in diborane, we observe that there are 2 kinds of bonds which are shown in the diborane, structure of diborane, that is the BHB bond. This is the banana bond which it is forming, and it is also called as the 3 center 2 electron bond. And we also look at the 4 terminal hydrogen atoms which are forming the BH bonds. These are called as the terminal hydrogens. They are different from the bridging hydrogen that is they are forming that is the BHB bonds which are there forming the banana bond. यहाँ तो यही है. 3. As you can see that there are different bond lengths of the BH bonds, the BB bonds and the BBB bonds. We also notice the bond angles are also bond angle in the terminal BHB is found to be 122, and the bond lengths, that is the BB bond lengths, are different from the BHB bond lengths. In this chapter we will be learning about the bonding in boranes, the bonding in diborane, that is B2H6. Typically we are explaining the 3 center 2 electron bond where there is a BHB bridging bond and BH terminal bonds, and different bonds in the boranes, that is the BBB bonds, the BHB bonds, the BB bonds and the terminal BH bonds. And bonding in high boranes can also be explained with the help of different kind of bonds which we will be discussing in the following, which will be discussing